Video, I want to say a few things about Monte Carlo tree search. Now, Monte Carlo tree search is used in the context of games, which are typically adversarial search trees. So we haven't talked about that in this course because I decided to talk about a few other things instead. Nevertheless, I want to say a few things about Monte Carlo tree search because it's being used in AlphaGo, and we're going to have a look at that system very, very soon. And so I thought, well, now's the time, since we're talking about search, to understand a little bit more about this thing. This is not going to be a long presentation. So Monte Carlo tree search is a heuristic search algorithm. So we know about heuristics, we know about search, but it's used in gameplay. So I say a few things about gameplay here in a minute. It was introduced in 2006 for the computer to play Go, but it's used in other games too. The key idea about Monte Carlo is that we have many games that we play, and so they're called playouts or rollouts. And the way it's being played is kind of really neat. It is partially based on what we know already, but mostly based on a random sampling of the search space. So let's have a look at how this thing works. So here is like an overview, and I'm going to explain each of these components. We start with selection. So like looking at our search tree, what might be a good move to expand to know more about. So we'll have a node over here, and we'll say, let me sort of like develop a child node. This is the one over here. And this is the cool part over here, which is a simulation where we sort of like say, okay, what if? What happens if I were to play a game from this node on? And we, by and large, make random moves. There are ways to bias them to halfway reasonable moves, but by and large, we make random moves. And then we'll see, did I win or not? And if so, great. I chalk that up as a win. If I lost, I chalk it up as a loss. So that's sort of like this idea of backpropagation. So let's have a look. Here is a sample tree. Again, we're talking about selection now. And what we have over here is we have a count. As part of this, running this algorithm, this simulation, I played 21 games and I won 11. Now this is for adversarial games, so there's these grayed out nodes. Those are the statistics for my competitor, for my opponent. So they happen to, in this state, they happen to win 7 out of the 10 games. So it always alternates. And so these things then represent moves. I'm over here. When I made that move, my competitor won 7 out of 10 times. They made this move, and I won 1 out of 6 times. I made this move, and I won 3 out of 3 times, and so on and so forth. Now, when we explore this tree, there's a key concept of exploitation versus exploration. That is a concept that happens in many, many optimization algorithms. The idea is, to a certain degree, we want to sort of like take advantage of strong moves. But a lot of times, we may not know whether something is a strong move if we don't have any data about it. So if over here, we certainly have more data about this node than about, say, this node over here, right? Because we only played 3 games. Now, the opponent lost all 3 games, so from our perspective, maybe that's a good move to make. But we just don't have enough data. And so a lot of times there's a bias towards early on doing some exploration to sort of see, what's up with this node? I mean, how powerful is it? What does it lead to? So in any case, in this particular example, we decide, okay, well, let me find out more about this node, and then follow the arrows, this node and this node. So we selected this node over here. We want to learn more about it. So what we do is we generate one successor, not all children's successors, but just one. And we initialize it with 0, 0, because we haven't played any games yet. I mean, this is a new node. So then we do the simulation. As I mentioned before, is we make random nodes until the game ends, until the goal state is satisfied, either I won or my opponent won. Again, you can use some heuristics to bias the selection of actions that look more promising, certainly, but don't spend too much time on it, because Monte Carlo tree search derives its power from playing many, many, many games. So in this particular example, I think we lost and we played one game. So now what? Well, we need to propagate this information back. So we're going to fill up, we're going to modify the nodes on the path back to the root. Okay, so so this is the data over here. We lost it, our opponent won it, and so on and so forth. It's better explained if we look at these things side by side. So this is what we had over here, and this is the slide that I just showed you. So we lost one, so white is ours, the grayed out one is our opponent. So 0 out of 1 game we won. But our opponent, again, so notice that all of these things get increased by 1. The denominators get increased by 1. And so we have our opponent won 4 out of 4, we won 1 out of 7. Their opponent won 8 out of 11, and we won 11 out of 22. So that's what we do by back propagation. And then putting everything together, using this example, we have, again, selection, expansion, simulation, back propagation. Very simple algorithm, right? So like just a few heuristics here that sort of like this tell us, should we use exploration versus exploitation? And then here's some minor heuristics about doing this, about picking better moves. But the thing is, the law of big numbers, if you play this enough, you actually get some good data. And so that's what this algorithm is all about. Alrighty, folks, that's it. See you next time.